Before we start, I would like to say a word about our AI and machine learning for healthcare summer school that we will run in September. So if you get very interested by our software tools that we are presenting today here, there will be hands-on tutorial sessions in the summer school where we go more in depth with all our tools, and also there will be lots of talks about the theory behind our research and what AI and machine learning can do for healthcare. And if you're interested, please go to our website and sign up for the summer school. It's from the 11th to the 15th of September, and we're looking forward to see as many of you as possible, as a lot of our content will be very, very tailored to clinicians, and clinicians are very interested in making AI part of their workflow. And the first step to that is our AI clinic, and I really welcome you to that. We run it together, the Van der Schaal Lab and the Cambridge Center for AI in Medicine. You will hear from our presenters about all of the state-of-the-art open source software that we have created in the past year or so, and have the chance in the end to discuss your questions with our speakers as well. So it's a really good way to get into what the center has to offer to you. Our main speakers today will be Professor Andres Flote, who is one of our co-directors of the center, and Professor Ian McKinney, as well as Dr. Thomas Callender, who I really congratulate to the birth of his child today. So it's really, really great to have him around as well for this talk. And we start with an introduction to the software in general and what the center is doing by Andres, before we dive mainly into SynthCity, which is a synthetic data tool that will be presented by Thomas Callender, and Evgeny Savelyev, one of our research engineers, will show a demonstrator about it, and then jump over to Temporal AI with Andres talking about longitudinal forecasting, Ian then going deeper into interpretability and what you can use these tools for estimating treatment effects, and then further demonstrators and how-tos by Rob, another research engineer of ours, and Evgeny, before we then go into the discussion. So with no further ado, I would like to hand over to Andres to introduce you to everything the center is doing in terms of software.
Thanks, Andreas, and welcome everyone to this second edition of the AI clinic run by the Cambridge Center for AI in Medicine, as well as the Van der Schaal Lab. Just to give you a couple of slides around the Cambridge Center for AI in Medicine, which Mahela and I started up a few years ago with support from AstraZeneca and GSK, really with the mission to develop pioneering AI and machine learning technologies to transform biomedical science, medicine, and healthcare. And importantly, this is really interdisciplinary research where ideas in medicine will drive innovations in machine learning AI, and conversely, machine learning and AI will drive a revolution, a step change in medicine. And we have 4 pillars of activity. Our first is around basic biomedical discovery, using ML as a discovery engine. Second, we have a lot of activity around omics integration. And the third area, which is the subject of these AI clinics, is around patient population studies and how we can use machine learning as decision support tools. And finally, an extension of that is to look at implementation to improve healthcare systems and home monitoring. But one of our main drivers really is to develop software that can be used by clinicians to enhance their understanding of disease itself, and also importantly to improve the care that patients receive. And with that in mind, a huge amount of effort in democratizing AI methods so that clinicians around the world can use these applications. So I'm just going to briefly summarize some of the activity that's happened in the Van der Schaal Lab in collaboration with CCAIM which are software platforms that are available now and are increasingly being used by clinical researchers around the world. So the first is temporal AI, which is a method to look at time series medical data. And I'll be explaining this in a bit more detail and providing a use case later. But effectively what this does is leverage time series data to predict patient response to treatment, identify optimal treatment durations, look at the ability to define the treatment effect at an individual level. And Owen's going to talk a little bit about that aspect of the work. In addition to that, there's an interpretability suite, which is a very comprehensive collection of machine learning interpretability methods that the Van der Schaar lab had been developing over the last few years. It's very exciting, and I strongly urge you to have a look at that. It really allows users to enhance the transparency and trust in ML models. And because of that, should improve collaboration between data scientists and clinicians, and again, in terms of implementation into the clinic. The third area which I want to flag up now, which will be discussed later in a bit more detail again by Owen, is autoprognosis, which, if you like, is the ultimate in democratization, where we're using AutoML methods. Again, this is the Van der Schaar lab developing this, to really use machine learning to optimize the implementation of machine learning in order to end up with predictive modeling of clinical scenarios. So, as I mentioned before, streamlining the development of diagnostic and prognostic detail models, enhancing decision-making process, but again, combining state-of-the-art machine learning with built-in interpretability. And finally, the generation of synthetic data. And I'm going to hand over in a second for Tom to give you some more details around this. But clearly, this opens up a whole avenue of opportunities to generate synthetic data to allow data scientists to work on clinical problems, and in many cases, allow inherent biases in data sets to be corrected and mitigated. So without further ado, let me just describe how these software platforms are being used already. So you can see on this slide the number of downloads and activity for each of these suites of ML algorithms. So it's clearly having real impact already, and we hope that with increased understanding, there'll be more uptake.
I will kick off. So thanks again for having me. I'm Tom Calendar. I'm a public health doctor based currently in London. And I wanted to take you through a little bit of how we've used synthetic data in a particular healthcare application and why I think this is a really exciting avenue. So what is it? The most important thing to understand about synthetic data is that they are new individuals generated by algorithm. The importance is the algorithm. If it's good enough, then it will maintain the different properties of an original data set so that you can use these synthetic data to do lots of original things. The ideal is that we can, in many situations, replace real data. And why might we need to do that? Well, Andres mentioned things like fairness and bias. So that's the kind of first step, is data augmentation. So take, for example, something like the UK Biobank, which is often used for prognostic modeling. The Biobank represents UK participants in the early 2000s and doesn't have very many people from anything other than a white ethnicity. But with augmentation, you can try and correct some of these biases, particularly if you have access to, through access to different data sets. But the bit that I'm going to really focus on today is privacy preserving data sharing. And we need this desperately within clinical medicine. If you think about most data, it's locked away in electronic health records. In some circumstances, you might be able to get access, but usually that access is extremely complex, time-consuming, and costly. And this has largely meant that most of this data is not really used at all. And of course, this is for good reason. It is extremely sensitive, so we need to be able to share it in a privacy-preserving manner. What I want to show you over the next couple of slides is how you can use synthetic data for privacy preserving data sharing. And this, as a result, means that we should pursue this area as something that we can go forward with and try and release synthetic data in different circumstances, because it really might allow us to rethink how we do quite a lot of medical research. So what we did, so this is me and Jiaji Chen from Mahela's lab. We took the UK Biobank and we thought, could we use something as complicated as the Biobank, which is a massive data set, almost 500,000 people, thousands of different variables, very complex structure between the different variables. And could we create synthetic data using specifically privacy preserving generators that is good enough for us to build prognostic models? And so we took as an example lung cancer screening, and the reason that we did that can come towards the end. But the first things first, we took the UK Biobank, we did a little bit of pre-processing, and then we used Synthicity that was mentioned to be able to create synthetic data sets. And we found that we could completely mimic the original components. So these plots, these are density plots that show you 4 different important prognostic markers in lung cancer. And you can see that the ADS-GAN, which is one of the synthetic data generators, was able to completely represent the original data set, even in the case on the bottom right here, where you're talking about cigarette smoke per day, which is actually, although this is a continuous variable, most people say that they smoke 10 or 20 or 30. So it's kind of categories. And the fact that we were able to mimic those categories is really rather remarkable. But this is something that's been shown in a smaller set beforehand. So we decided we would take this a bit further, and we thought, well, can we actually use it for exploratory analyses and prognostic modeling? And so this just gives a plot for principal component analysis, as it was an easy way of showing some of what we were doing. And the important thing to note on the plot is not necessarily the values per se, but the fact that all of the synthetic data generators mimicked the pattern seen in the original UK Biobank, which was that essentially after about 4 principal components, that was enough. And so why is something like that important? Well, it means that if you didn't have access, you could use synthetic data to be able to do quite a lot of your initial exploratory analyses before even thinking about it. And then taking it further, we then decided to build both Cox models, and we used DeepHit, which is a neural network-based survival analysis method, to build new prognostic models of lung cancer in these synthetic data sets. And although, as you might expect, because it's not the same as the original data set, you do get a drop-off in the predictive performance. We found that when we were analyzing the data set, the same features were important in the same order, such that if we had just been doing variable selection, we would have been able to do all of it with the synthetic data set without ever seeing the original version. And so if we think about it, there are multiple different ways it can be deployed. So I've simplified it slightly for this case, and I just wanted to talk about 2. The first would be a no release scenario, and that itself can be broken down even further. You can have a scenario where you're never going to see the original data set as a developer. And in that case, we've shown that you can use synthetic data for quite a few analyses, but you have to be quite cautious about some of the conclusions you were drawing. More realistically is a kind of partial no release scenario where the developers never have actual access to the original data set, but they have the ability to run their code on the original data set. And with the paper that I've just been showing some of the analyses from, you could actually do almost everything you need for prognostic modeling without ever seeing the original data set, so long as you were able to run your code. And I'll come back to what that means in the future. And then, of course, there's a delayed release scenario. And in some respects, this is a bit counterintuitive. Why would you need synthetic data if you're going to go and get access to the real data in the future? But I can give one example where, for example, we got a grant where we were looking at real world data from particular hospitals around the UK. And we really didn't think that this would be a big problem, as we have quite a lot of experience with particular hospitals involved. But we found that the actual data, when we finally got it, was of such poor quality that we couldn't do any of the analyses that we had hoped we'd be able to do. Now, if we'd been able to have a synthetic version of some of this beforehand, we could have completely changed, and the whole grant changed all of our plans, and rapidly de-risked, but also sped up the project. This can be applied in lots of different ways. You can start doing your analyses way in advance. We know, for example, it can take 6+ months to get access to some of the big data sets. Start doing everything, seeing what you need, playing with your hypotheses, and then when you get access to the real data sets, you're able to actually produce results much, much faster. In an age where it takes years to get access, or 6 months to a year, if you don't have this kind of delayed release response, actually it can be an impediment in some respects to being able to get things out in a timely manner. COVID would have been a good example of that. If we have to wait 6+ months, then how are you going to be able to do the analyses that we need in real time? And obviously in COVID, there were exemptions made, but those exemptions are not usually available, hence why this is important. So I want you just to imagine one possible future. In the UK, we are thinking about rolling out lung cancer screening at a national level. And in order to do this, we have to know who is going to be at high risk of lung cancer. Those are the individuals that we will screen. At the moment, what we do when we build risk prediction models is essentially a cottage industry. There are a few people around the world who are interested in this kind of thing. They produce a few models. Perhaps we test them. If the models are there, great. If they're not there, well, we think about a different route. But this is quite an inefficient way of doing it. And in a possible future, you as the National Screening Committee, together with the NHS, put together the data sets you think are important. You create a synthetic version of some of those data. You release the synthetic data to a competition so that you get the best possible outcomes. You then can test it on data that you've held back that's real. You can then see if you can improve it based on all of these different things. And then based on that, you can implement actually the best algorithm rather than a little bit of our current situation. This is particularly important in countries where at the moment you're having to use algorithms that are built elsewhere because of lack of actual data. And so I do think that this can really lead us somewhere new. If you're interested in doing more of it, I would highly recommend you start with Syntheti. So I am by background a clinician, and although I'm coming to the end of my PhD, without something like Syntheti, you would find it extremely challenging to be able to put together the synthetic data. This is because it's not a straightforward procedure. There are lots of different ways of doing it. And the advantage of something like Syntheti is that it presents it in one single format so that you can try different methods and you can see how you can improve their quality. But I'll leave that to Evgeny, who's going to talk to you a lot more. So thank you very much.
I am Evgeny. I'm one of the research engineers at Vandana Shah Lab and the Cambridge Center for AI in Medicine. Simply, I will talk about synthetic data use cases I can done with Syntheti. So the best place to go to see all of our software is github.com/VandanaShahLab, one word. And everything is there. And at the very top, you can see all the different software which we have discussed today. And the links here will take you straight to the right place. As Tom has explained, we have this library called Syntheti, and it allows us to generate synthetic data. Here is a sort of interactive demonstrator which illustrates how this could work. In the actual library, don't expect to have all these fancy interactive bits. They will be more data input, output kind of thing, but this shows quite nicely what we are able to achieve with this. So let us say that we have some kind of data in tabular format like this, some kind of medical data. Don't worry, this is not real data with actual patients that we're showing, so there's nothing like that there, but let's pretend that this here is some real data that you have. So let's say there was some personal data that we removed that, and then we converted categorical and text data into numbers. Everything is numerical, like so. So here's our real data set now. I will then talk about generating synthetic data for 3 different cases. So privacy. So you want to generate synthetic data to share it with someone, but obviously you don't want to release real patient data. Let's generate good synthetic data, which is private, and then share it with somebody else. Number 2 will be domain adaptation. That's when we're trying to match your data to generate synthetic data that looks more like some other data set, let's say from a different hospital. And then finally, fairness. Obviously, there are ethical issues around protected variables like ethnicity. How do we generate synthetic data which correctly represents the protected variable. So more details on that. So first of all, case number one, privacy. So for that, a good model to use, which is available in SimCity, it's ADS-GAN or ADS-GAN. And let us explore this particular model. Now, the issue with generating private synthetic data is that there's always a trade-off between how faithful to the real data the generated data is. Perfectly faithful would be exactly the same, but quite faithful, very similar and captures most of the features of the data, versus how completely private it is, and it's completely impossible to kind of tie it back to real data. So there's always a bit of a trade-off going. And there's a way to measure this trade-off with metrics as shown in this diagram. So Wasserstein distance, if this is closer to 0, it means that the synthetic data is very similar to real data. If it's high, it's very, very different. And epsilon identifiability, which is a metric which actually kind of follows GDPR privacy guarantees, is how private the data is. If this is high, it's very easy to identify the true patients from the data or infer them from the generated data. So that's not private, but since 0, it's private. This model, ADS-GAN, has actually a controllable parameter, which can allow us to look at the trade-off between these two different things, privacy versus faithfulness. So if we set this parameter more on the faithful side, we generate the synthetic data. You can see it's quite close to real data, which sits in this corner. But it's less identifiable, so a bit more private and still quite realistic. So there's an example. We have generated some synthetic data, which is more private, and it is quite realistic. So if we look at the distribution of different features, they're actually quite similar across the board to the real data. We can then adjust this parameter and make the data a lot more private, generate that. And you can see it lies in a different area of this chart. It's a lot more private, but somewhat less like the true original data. And we can see that now there are more differences. So it's not quite as perfect of a match for certain variables. Synthetic data, blue and red, are quite different in some cases. And we can even try all the different cases of these parameters and see where that lies on this chart. Now, another thing worth noting is that a common thing that we want to do is we want to evaluate our synthetic generated data on some kind of downstream task. So, for example, we want to take some kind of target variable in our synthetic data and do some prediction and see whether the predictions perform similarly to the real data. That's a very common way of evaluating our synthetic data, and this is also available in SimCity and is also illustrated in this example, in this demonstrator. And there are some metrics you can look at to evaluate this. I will not go into too many details, but this is a very common way of evaluating how good your synthetic data is, and this is available in SimCity. Now let us move on to the second interesting use case of synthetic data, and this is domain adaptation. Let's say we have a data set, our own data set here at the top. And then there's another data set, let's say from another hospital, and we want to generate some synthetic data that's more similar to that other data set from a different hospital, perhaps the different types of patients. We want to get something closer to that. Let's call that the target data set. So we'll select some target data set. There it is, that's another data set. And we can then use a model called RadialGAN, also available in SimCity. And it will allow us to generate the data that is more similar to that target data set. So let's say we generated it here. And what we can see on these charts now, just give a second to appear. So in red is our internal original real data. And in magenta is this target data. So you can see some features, for example, ethnicity distribution is quite different between red and magenta. And then we've generated this cyan or blue, which are synthetic data, which uses the information from our internal real data, but matches it more closely to this target data set. So you can see cyan and magenta are quite close. And in fact, we can, for example, have a look. So this is an example of class balance, but also if we select, for example, like number of children, this feature wasn't actually present in our internal data set, but was present in the target data set. And we can actually see there's no red here, it wasn't present at all, but features have been generated by this radial gamma in the target, in the synthetic data to match our target.
Let's change tact a little bit and talk about this problem of time series analysis of clinical data. So I'm sure all of you will be aware of the types of data that we deal with on a day-to-day basis when looking after patients. So they are made up of static data such as gender, ethnicity, genetics, event data, things that happen, hospitalization, a cardiac event or injury, and time series data, whether that's from wearables at home or encounter-based data in clinic, but that could be medications, physiological parameters, and so forth. And really, we're faced with a challenge of explicitly or implicitly answering the following key clinical questions, which is, what is the individual risk of a certain event happening? And obviously that's going to determine how we approach an individual patient. Can we say something or predict the trajectory of an individual over time? How are they likely to change? Are they going to decline? What are the likelihood of remission, for example? And specifically, what are the medicines that a person is taking that are doing any good? And conversely, what would have happened if patient A had had medicine X instead of Y? So this idea of being able to understand the individual treatment effect and the potential for a counterfactual estimation are really intrinsic to how we manage patients at the moment. And so this package called Temporal AI that Yevgeny is going to, has developed and is going to show you in a bit, is really a simple method to try and address these key clinical questions. And so it's structured very simply as in the following way. You can see that the clinical data is inputted. There's some degree of pre-processing for both static and temporal data sets with feature scaling and imputation of missing data. And then there is a suite of software that's been developed by the Van der Schel Lab and others to allow you to explicitly analyze the time to event, to make a time to event predictions, to understand or infer the treatment effect estimations on an individual patient, and to predict for an individual what's going to happen in the future. And so the outcome of this really powerful suite of programs is to generate actionable intelligence and to be able to predict, therefore, individual risk, clinical trajectories, and treatment effects. So as I say, Yevgeny is going to show you this in action in a bit. I wanted today just to give you a use case, which is around cystic fibrosis, which many of you will know remains the most common life-limiting genetic condition affecting Caucasians. Is a very useful example because it affects multiple organ systems, predominantly the lungs, but also the liver, intestines, bones, and so forth. Death and morbidity and mortality is dominated by chronic inflammatory lung damage. So cystic fibrosis causes this really thick secretions and is due to a failure of this protein, the CFTR, cystic fibrosis transmembrane regulator, that controls the amount of salt and water handled across epithelial layers. So one of the problems with cystic fibrosis is the presentation and the clinical trajectories are incredibly variable. But what we can say is that the number of complications increases over time. Here you can see the distribution for the UK CF registry, which covers 99.5% of all people with cystic fibrosis in this country. And you can see that as the person's age increases, there are increasing numbers of complications. And you can see the whole range of potential complications in addition to lung disease here measured by spirometry, FEV1, and the requirement for lung transplantation or sadly death caused by respiratory failure, certain infections, liver disease, impaired glucose tolerance and diabetes, allergic bronchopulmonary aspergillosis, hearing loss, depression, and so forth. And so it seemed the perfect opportunity to test some of these cutting-edge machine learning methods to try and understand whether we could predict features and temporal trajectories of individuals with CF. This is work done by Timing and Chang Qi in Mihaila's lab with some input from me. So just to put this into a clinical context, then the kind of overarching aim was to see if we could use machine learning to support clinical decision making. And in this cartoon, you can see a hypothetical trajectory of an individual born with a particular mutation in cystic fibrosis, and then developing complications, for example, Pseudomonas infection, the onset of diabetes, other multi-drug resistant infections, and really being able to use these methods to try and predict what are the risks of events occurring, and indeed the competing risks between two different events, to try and understand and forecast clinical trajectories, and importantly, to understand and predict treatment response. So just as an aside then, because this is a Mendelian genetic disorder, it's also an opportunity for us to understand how we need to, in many cases, pre-process the data to make them suitable for ML approaches. So there's over 1,500 disease-causing CFTR mutations. Impossible to encode those individually. But what we've been able to do is leverage global international data that gives a prediction of pancreatic insufficiency when a particular mutation is found in combination with a null mutation. And so this allows us to infer the activity of the CFTR protein based on the incidence of pancreatic insufficiency, which we know is almost exclusively related to genotype. And so that allows us to then stratify patients by CFTR dysfunction score. And you can see that for many of these complications, there's a correlation with the degree of CF dysfunction. So pancreatic insufficiency, this is the UK data, diabetes and liver disease. It's not perfect, but there is some relationship. Importantly, when you do this analysis for lung disease, everything falls apart. So actually predicting the trajectory of lung disease in CF is impossible based on age or CFTR dysfunction score. And you can see here the scatter plot, very little structure to this. And that's because environment counts for over 50% of lung function decline, and CFTR mutations account for only 30% of the remaining genetic contribution. So there's lots of unknowns that contribute to this. Nevertheless, temporal AI is able to very accurately predict future FEV1s using a recurrent neural network architecture, suggesting that there are features and information in the clinical data that allows accurate forecasting. What temporal AI also does is to provide interpretability to these predictions. And this is at an individual level. I'll show you that in a bit. And here I show you aggregated feature importance related to respiratory failure. And I show you here the features with the highest importance. And this is the contribution of data from year 0, as in like now, and historical data sets going back up to 9 years. And also the features with the most variable importance over time. So again, these recurrent neural networks will use information from now, but also historical information. So this is incredibly useful in terms of sense checking with known features that are associated with respiratory failure, but also as a discovery tool to look for potentially causal relationships. One of the other things that the temporal AI does is to cluster patients around the predicted temporal trajectories. And this allows us to discover clusters of patients behaving longitudinally in a similar way. We've been able to allocate individuals very cleanly into low, medium, and high risk clusters. You can see here the Kaplan-Meier curves are strikingly different. Importantly, we can see these change over time. And so here you can see in the stars, the data for patients each year for 9 years. And you can see how they move from a low risk to a medium risk to a high risk cluster in this latent space representation. Importantly, while there are statistical differences in many of the features at time zero between patients in low, medium, and high clusters, there's enormous overlap. That's to say, in clinic, you wouldn't be able to, with confidence, predict where someone was going to be in their risk cluster. So actually, we believe that this enables and supports clinical decision making, and by finding new information which isn't apparent, obviously, at the moment. And just to give you one example of a single individual, and you can see this is age along the x-axis, and you can see the risk of respiratory failure in red, how the FEV1 declines in blue, and the days of intravenous antibiotics in green. And so you can see that each day, each time point, the algorithm is updating its prediction. And at the top, you can see how the patient moves from cluster 1 to cluster 2, and then eventually to cluster 3. And at each of these transition points, we can look for the individual features that have been used by the algorithm to affect this transition. So again, very useful individual information around potentially causal relationships. So in summary then, Temporal AI provides decision support. That is to say, we can see clear ways in which this could be used in the clinic, but also biomedical insight. And you'll see in the preprint that's hopefully coming out in the next couple of weeks, how we've been able to discover new associations in cystic fibrosis through this very powerful methodology. So I'll stop there.
So first, let's have a look at Temporal AI. Here, our time series-based piece of software. It's a machine learning-centric toolkit for medical time series, basically, as Andreas has talked about. Just very briefly, here, there's a very nice README that explains big picture overview of Temporal AI, their key use cases, key tasks, so to speak. Survival analysis, so predicting the risk for a particular event is one. Treatment effect, so how would a particular target variable for a patient behave differently depending on different treatment plans is another, and just a more basic just time series prediction, predicting some kind of target variable over time is another one. All the software that we talked about is in Python, which is probably the most common language in this sort of area of data science, medical data science, machine learning, and so on. It can all be installed very simply with pip install Temporal AI or pip install SimCity and so on. We always provide a lot of basic usage examples here and a list of various methods with links to reference to the right papers as well. And for Temporal AI, you can find all the links there, but we also have very good documentation, similarly for other libraries as well. It provides overviews, various user guides about what format the data is, how to use the software, how to extend with your own methods, even things like that. So always have a look at the documentation. Most of the things are there. And we always also provide in the sort of form of Colab Python Jupyter notebooks, just examples of going through scenarios of I want to do this is how you do it. You can just run it straight there, and this I think is a very good way to getting started. So if you are yourself familiar with things like Python or know someone familiar with that, very easy to get started is the key. And finally, there are always issues. There's always an issues page where you can submit any bug reports or feature requests or anything like that. So this is how to get started with something like Temporal AI.
So I'm just going to go through two concepts quickly and show how they're dealt with in the tools that we're describing today. The first is interpretability and the second is individual treatment effects. So interpretability is difficult because actually it doesn't really have a consensus definition, although that's starting to change. And there's a 5-point definition here that has been proposed by Mihaela's group. So what interpretation actually means when we're considering a model. Here you see a model where we're trying to discriminate dogs and cats. We use data like an image, where in order to interpret that model, there are several different factors that we need to consider. So first of all, feature importance, understanding what features in the source data set are important in a decision-making process, and that can be handled with things like a saliency map, for example, that you see here, picking out the key features of the dog that are relevant. The second is similarity classification. In other words, trying to understand what other instances in the data are most like the query instance. So what other dogs might look like. That's relevant in a medical data set for looking for similar cases and understanding what cases are most like the index case that I'm querying. The third point is probably the most important from an interpretability point of view, and perhaps the most understood concept when medics use the term interpretation, and that's we use the model to try and gain a mechanistic understanding of the process that we're trying to model in the first place. And that's perhaps the hardest because it requires some domain knowledge to interpret or use the features that the model is looking most at. The fourth is if we can infer specific rules or laws from the process by defining a model. And the fifth is a more transparent approach to try and understand and pull out very transparent risk equations so we can understand exactly from the model how it is making the prediction that it is making. And each of these components are important when we consider interpretability. Knowing the features that a model is looking at, as I mentioned before, does not necessarily tell us something about the process that we are trying to model. And that's been clear because if we create a model that can very accurately predict or interpret something, the features it's looking at can be the same in highly performant models and in those that don't particularly work well, as you see here. So the same features from this image are used by models that can clearly interpret what the animal is and those that clearly can't. So we have to be careful when we try and use the salient features to understand the underlying process. And those are two different sequential steps in model interpretation. But it is clear that interpretability is extremely important, and this comes from clinicians, so from the people that are probably listening here, the audience. And when asked what are the most important features of a model before it's incorporated into practice, understanding feature importance at the individual level is forefront there. Instantial explanations, so understanding what other cases are most similar to the one that I'm trying to predict. Some form of quantifiable uncertainty is important as well. Temporal explanations and how that explanation changes in time series data has been brought up as being critically important. The sort of transparency that I've alluded to is extremely important too. And they're all important to allow avoidance of alarm fatigue. And that is basically the concept where models don't get used in practice because they continually alert you to do something that you don't understand why you should be responding to it. And consequently, over time, as you see in the graph on the bottom, clinicians just end up ignoring it because they can't work out why they're being told to do what they're doing. From an interpretability perspective, the inherited wisdom was that actually interpretable models did not perform as well as those black box models that could give better performance. And that was basically the inherited wisdom that was established, but that's beginning to change, where it's clear that we can now build models that are not black box that perform as well, or that we can interpret black box models better. And that's moving us away from the inherited wisdom that things cannot be explainable if they are to work well, to the point where actually we can have highly accurate models that have fidelity but are comprehensible and therefore trustworthy and much more likely to be adopted as a consequence. There is a need to understand models, so not only can we interpret them, but we have to be able to interpret them. It's increasingly required for regulatory approval, as you see here with GDPR, that now specifies that meaningful information about the logic has to be available. The bottom point is the most important one here that I have made so far, and that is in the context of being able to identify bias and debug a model. You have to be able to understand what it's looking at, not necessarily why, but you have to understand what it's looking at. And there are apocryphal examples such as this one, whereby models can be developed, and only because they're interpretable and we can understand why they're looking at what they're looking at, is it possible to understand that the model's not being built correctly or there's information leak. And this is the apocryphal example where saliency maps were able to identify that a skin melanoma predictive model that was trying to interpret images of melanomas was actually incorporating and using the pen dots that were put around the melanoma in the first place. So In order for a model to be interpretable, it requires a set of tools and it requires specific model types to be used. But essentially uncracking those models that are not so interpretable is now feasible with the sort of tools that are being made broadly available through Mihaela's group. So the interpretability suite here gives you multiple different interpretable tools that can be bolted onto other models or used themselves to facilitate the sort of interpretability that I've described so far. So it's clearly important. It's clearly accessible in a way that it didn't used to be. And it's now being democratized because the tools are available and should be used. Second thing I wanted to talk about briefly is individual treatment effects. Now, for any clinician, treatment effects basically underpin everything we do. We have to know whether the things we do, whether they're treatments or interventions or processes, whether they actually work. And for that, we rely upon typically randomized evidence or evidence from randomized clinical trials. But within a clinical trial, you have a heterogeneous population. You've got a group of people, some of whom will respond more than others. And what a trial effectively tries to do is estimate by randomization, control for confounders, tries to estimate the average group treatment effect of the entire sample. So if I give one group a treatment, one group not, what's the average effect and is there a difference? We use that evidence to underpin most of what we do. That's modern evidence-based medicine. However, this has got limitations. As you see in the bottom, we compare group means. It restricts to that group level. Trials are expensive, time consuming. We only look at one intervention at a time. And the way the emphasis we put on these is they're imperfect. They're gold plated. They're not a gold standard. And the reason is that we take a disease population. We only include a minority of patients from that disease in randomized trials, usually the most homogeneous group we can to maximize signal to noise ratio. Then we take that result and we wildly extrapolate it back to a huge population that were never included in the study in the first place. So our evidence-based approach is fundamentally undercut by that. And you can see on the right, the proportion of individuals that are excluded. So the proportion of individuals with any given disease that are excluded from clinical trials, and a quarter of the trials exclude nearly 90% of the patient population. So this is a tiny proportion on which we generate the evidence and then extrapolate it back to everybody. So a way around this is to try and estimate individual treatment effects. So not this whole heterogeneous distribution, but for any one individual within that distribution, could we estimate what the treatment effect of a given intervention would be for that individual? And this requires us to estimate from observational data something called counterfactuals. And that is in essence for that individual, what would have happened if they did get treatment or if they didn't get treatment. And obviously only one of those circumstances will ever be observed for that individual. They'll either be treated or not. But what we want to understand from observational data is the counterfactual, the opposite scenario. And if we can estimate that, then we get an individual treatment effect for that person that we're actually trying to treat with all of their complex comorbidities that would never be taken into account in a randomized study. So that's now increasingly possible. So estimating individual treatment effects from observational data and that counterfactual process can be estimated using causal inference models. That can be done using time series data. And we're going to describe some of the tools here that can be applied through Tempora AI that Andres has already referred to. So essentially by using causal inference, you can estimate what that likely individual treatment effect is for any given individual that you might be interested in treating with any given intervention. Main question is, can this actually work? In other words, can you use individual treatment effect estimation to sum up an average treatment effect for a population? And if it can work, you'd expect that grouped individual treatment effect estimates to come up with the same answer as a randomized clinical trial. And for some methods that has been demonstrated. So for one of the methods that's included in Tempora AI, you see here, the LDL cholesterol lowering effect that was seen in the heart protection study can very tightly be estimated using individual treatment effect estimation from observational data, in this case from AHR records that were in the CPRD resource. So this can be used to gain similar RCT level evidence that we spend a lot of time and money generating on a tiny fraction of the population. So another thing to consider is that for individual treatment effect estimation, and indeed for many other prediction methods, there isn't a perfect model that will work best in all circumstances. So which model should I use for my individual question, for my individual data set? Well, this has been systematically looked at, and you see the summary results across 77 data sets here using different methods to try and identify, in this case, a causal inference model, which model would work best. Is there a single model that works best in all circumstances? And as you can see, the answer is no. And perhaps not surprisingly. And consequently, what's necessary is to find out what the optimal model is for the data set and for the question in hand. And that's where AutoML comes in. So this allows us to apply multiple different models to the same problem and identify which one is going to work in that particular context. So Tempora AI allows us to do that for time series data in the same way that a recent released model, Autoprognosis, allows us to do for static models for prediction. So Autoprognosis allows you to take a data set and compare with cutting edge ML methods, also retrospectively including simpler models, also including interpretability estimates. It allows you to look at prediction methods and compare and find which one's the best. And in the same, conceptually in the same way, for time series data, Tempora AI now allows you to do that. So both for the causal inference approaches that I've mentioned for estimating individual treatment effects, but also for applying interpretability to those, so you can understand not just what intervention would work for my patient, but why, and interpret that. So I'll stop there in the interest of time and pass on to Rob, who I think is going to give you a real world live example of it.
Great. So yes, this is again the landing page on the Van der Schaar Lab GitHub that Evgeny showed you. I'm just going to click on the interpretability page, and that takes you to the home page here for interpretability for the lab. I won't, in the interest of time, I'll skim through this really quickly, but there's lots of good information here. It's a really great sort of central hub for all of the interpretability methods developed by the lab. There's some background. There's another introductory video that if you're interested, I encourage you to watch. I'm going to go through the interface very, very shortly. That's going to be the demonstration today. But yeah, we can see they've got this list of all our different explainability methods, and this flow diagram you've seen a few times today shows you, when you'd want to apply each of the methods. We also sort of break down here, for what data you want to use the methods and what type of explanation each of them gives you. So it's sort of your way of navigating through the lab's methods to find the right method for you. I will just very briefly point out, we've developed a common Python interface for some different interpretability methods, and we've got notebooks associated with a few of these different methods. So if you want to use Simplex, I encourage you to click on the tutorial number 1, implement Simplex, and that shows you super simply how to use this yourself from scratch. It's a very simple workflow. All you're doing is initializing an explainer, step 1, fitting an explainer, step 2, calling the method explain to get your explanation, and then you can get a summary plot after that. So if you do that behind the scenes, you can then actually output your explanation into the interpretability suite, which I'll take you through some examples we've got pre-programmed in. So there are 4 different explainers available in the interface. We've got Simplex, Dynamask, SHAP, and Symbolic Pursuit. SHAP is an external method developed by the wider ML community, and the other 3 are all Van der Schaar Lab methods. Simplex is primarily an example-based explainer. It works both for tabular and temporal datasets. Dynamask is specifically for temporal datasets. SHAP is static and tabular, and Symbolic Pursuit is an interesting model where it basically approximates the black box model with a closed form mathematical expression, so you can see exactly what would be going on, and basically is approximating the black box with a white box, and that's used to produce some feature importances and also feature interactions, which is very exciting. So I won't go into very much detail on how each of these work, but you can see in the Simplex demonstrator here, we have a test record here. We're looking at the famous iris data set. So we're classifying different types of iris species, the flower. and we've got a sepal length and a petal length and all these different features. And what it's saying is, given that test record, we've separately given the explainability module a series of other records to look at, and it's saying these 5 here are the most similar. So if you imagine this in a clinical setting, you've got a patient, and these are the most 5 similar patients, and they're similar with regards to the red features. The blue features make them less similar, and we're looking at the example importance here. So something that's 50% similar is the most important one, and we can compare and contrast the features and the predictions to see whether or not they agree. Do we want our test record treated in the same way that our corpus members were treated here? So that's the example based. You're looking at similar examples. This works tabular, time series, different data sets, different models, and you can upload your own explainer on this tab. Very quickly, moving on, we've got Dynamask. So this is temporal explainability. Here you can see different features 0 to 5 and different time points across the bottom. So for our data set that I won't go into details, but it's explained here, we've got all of our different features, and we can see the different regions that were important for making the predictions at different time points. And we can also smooth that to make it less choppy, so we can get a broader sense of, feature 0 was important across the sort of middle period, and 4 was important a similar period, and then very unimportant towards the end. Again, different data sets, different models. SHAP. So here we can see the sort of Shapley values for how important each feature was when classifying each of the different classes. So it's super simple. The bigger the bar here, the more important that feature was to classifying it there, classifying it as that class. Again, we can look at different models and see the different representations of that display. Finally, symbolic pursuit. So as I mentioned earlier, this is our closed form mathematical expression that is approximating our model. It looks a little bit scary to look at, maybe, depending on your level of maths, but the important thing is it is defined. We know what happens at, we know what happens here. We can explain it very explicitly, so we'll know exactly what happens when we put in our feature values to get out our prediction, and we can see exactly why in terms of feature importance and the feature interactions. So I can put any input value I like into the boxes here, and it will update. The values have changed very slightly for the minor tweak in the value there. You can see our symbolic model, our symbolic pursuit model is predicting a classification of 1 for this input, and so is our predictive model. So they're in agreement, and that's a very important thing to check. But then we can see it's the petal width that was the most important feature here for making that prediction in our symbolic model. And so we assume, because there is a very good approximation, we assume in the predictive model as well. And the feature interaction, similarly, we can see what features correspond with what other features as an important pair in this matrix. We can see, given a certain petal width, the petal length is also very important. So that was a very quick tour of the explainability software, and I'll hand you back.
Thanks, Rob, and thank you to Tom and Owen and Yevgeny as well for some great presentations. We're going to move into the Q&A session now. Please, if you have any questions, to type them into the chat box. We'll get to all of them. We may need to answer some of them offline. Let me start with the first question, though, from Simone. Despite the challenges with using electronic health records, EHR data is the primary source of medical time series data. Does Temporal AI have any features that facilitate the incorporation of EHR data? I'm going to hand over to Mihaela, who's going to take this one.
Thank you. So thank you, Simon, for this. Of course, there are many features of electronic health records. One of them is the fact that the data is irregularly sampled, so the patients just come to visit their clinician whenever they have a particular symptom. So dealing with irregularly sampled data is something that we are able to handle in the TemporAI package in some of the methods that are incorporated there. Another feature of electronic health records, as opposed to other data sets that are curated for research, is that they are noisy. And they have all sorts of potential, not only noise, but also errors and bias. We are working as we speak in the Cambridge Center for AI in Medicine to release a new package focused on assessing and improving the quality of data. It is called data-centric AI, and we hope at the end of the summer to be releasing such a package. So these are some of the features that we have that deal with this real-world data, and we hope to incorporate more in the future.
Thanks, Mahela. Let me take the next question then from Leka. My concern with using synthetic clinical data is similar to the concerns raised by generative AI models. How can we be certain that all the data that it generates is accurate and prevent bias accumulation, especially in large data sets? I think, Mahela, you're going to take this one as well.
Yes, so thank you very much for this question. So this is definitely a very clear concern. Like you say, we see with ChatGPT and the large language models that there is a lot of chance for hallucination. This is happening, and this is possible with the type of models that are included in our open source software, SynCity, for generating synthetic data. However, because we anticipated this type of situation, SynCity also comes with a tool to assess the quality of synthetic data. So we not only have generative models, like for large language models ChatGPT has, but we also have an assessment tool where the quality of synthetic data is assessed with respect to its biases, representativeness, and its ability to generate relevant data that covers the original data correctly, rather than provide hallucinations like ChatGPT does. If you are interested to see more about that, I invite you to take a look at the extensive documentation that SynCity comes in and look at these assessment models for synthetic data.
Thanks, Mahela. In the interest of time, let's do one more question then. This is from Hanad. How do you balance, or how do we balance model accuracy with realistic clinical applications? So is there a way that we can limit the number of variables at the point of clinical use without losing prognostic accuracy, or is this simply a trade-off we have to accept?
So thank you very much for this question. I think, like you rightly say, there was a very good talk about this a few sessions ago by Tom. What is an advantage of the autoprognosis package that we have developed together, this autoprognosis 2.0 package that we have developed together with Fergus and Ern, is that you have the ability within the autoprognosis 2.0 package to try different number of features and different models associated with it, and do feature selection as well. So it is then up to the clinical researcher to really investigate with these tools, the data set they have, understand what are the relevant features as discovered by the different machine learning models, and select the ones that lead to the best performance given the number of features that they looked at. And the concrete example, again, in Tom's case, was that while a regression model needed a lot more features to achieve a certain desired level of clinical performance, with fewer features, he was able to achieve the same performance. And the reason he was able to achieve the same performance using autoprognosis is because of the nonlinear interactions between these fewer features, which were indeed modulating the correct prediction. However, for different diseases and different data sets, the answer may be different. So this is an analysis that our autoprognosis enables, but the answer may be different for different data sets and different clinical use.
Thank you, Mahela. Is that all the questions? I think that's all the questions. Again, thank you very much to all the people that have presented. Thank you all for your time. We'll have another AI clinic in the next few months. And again, all the details around the software packages available on the Van der Schaal website. And again, very happy to answer questions offline as needed. So thank you very much.
Last reminder that we will have our summer school. If you think that what you've heard today was really interesting and you want to hear more about it, the summer school is the best place to go to. It's in September. You will hear our speakers that we had here today there most likely as well, and there will be hands-on tutorials for that. And after we have done with the summer school, we will also be back after our summer break with the Revolutionizing Healthcare series. You can see this AI clinic tomorrow on YouTube as well, and feel free to share it with all your colleagues. If you have any more questions, you can find us online in the center and the Van der Schaal lab to send us your questions, and we will get back to you. Thank you very much for coming again, and have a very good evening.